Welcome back. Last episode, we finished the standard integration toolkit with partial fractions. Now we change the question. Instead of asking how to integrate, we ask whether an integral even makes sense. The setting, improper integrals. There are two ways an integral can be improper. 1, the interval is infinite. You integrate from some point all the way out to infinity. 2, the integrand itself blows up somewhere in the interval. A vertical asymptote. Either case, the ordinary Riemann definition we built in episode 2 doesn't directly apply. The fix is the same in both cases. Define the improper integral as a limit of ordinary integrals over shrinking pieces of the bad interval. If the limit exists and is finite, the integral converges. Otherwise, it diverges. Today we'll define everything precisely, build the p-integral table that every analyst knows by heart, and learn 2 convergence tests that decide the question without computing. By the end, you'll see why finite areas under infinite curves are not just possible. They're the foundation of probability, gamma, and pretty much all of mathematical physics. There are exactly 2 ways an integral can be improper. Type 1 is the infinite interval case. You write something like the integral from a to infinity of f of x dx, integrating from a finite left endpoint all the way out to infinity, or the integral from negative infinity to b of f from minus infinity up to a finite endpoint. Or, both at once, the integral from negative infinity to infinity of f. The interval is not a bounded closed interval like Riemann's definition assumed. Type 2 is the unbounded integrand case. The interval from a to b is fine, finite, and closed, but f has a vertical asymptote somewhere in it. The standard example, the integral from 0 to 1 of dx over the square root of x, the interval is the humble 0 to 1, but the integrand 1 over the square root of x blows up at 0. It's not even defined at the left endpoint, and it grows without bound as you approach. Why does this matter? Because the Riemann integral we built in episode 2 assumed 2 things, a bounded closed interval and a bounded integrand. Either kind of improperness breaks one of those assumptions, and the definition no longer applies as stated. We need a new mechanism. The new mechanism for both types is exactly the same idea, take a limit. Integrate over a tame, ordinary piece, then push the boundary toward the bad spot. Here's the definition. For type 1, the integral from a to infinity of f of x dx is defined as the limit, as b goes to infinity, of the ordinary definite integral from a to b. You pick a large finite upper limit, compute the integral with the techniques we already know, antiderivative, fundamental theorem, then let that upper limit slide to infinity and see what happens. If the limit exists and is finite, we say the integral converges to that value. If the limit is infinite, or oscillates and doesn't settle down, we say the integral diverges. For type 2 with an asymptote at the lower endpoint a, you do the same thing on the other side, integrate from t to b where t is just past a, then let t approach a from the right. Same definition, same converge or diverge dichotomy. For the two-sided case where both endpoints are infinite, the integral from negative infinity to infinity of f, you have to be careful. You split the integral at some finite point c and require both the left half and the right half improper integrals to converge on their own. You're not allowed to take a single limit that lets the two infinities cancel. That last subtlety matters. The integral from negative infinity to infinity of x dx diverges under our definition even though the symmetric limit, the limit as r goes to infinity of the integral from negative r to r of x dx equals 0, exists. The symmetric limit is called the principal value. The strict improper integral requires more. First example, the canonical convergent improper integral. Compute the integral from 1 to infinity of dx over x squared. Apply the definition. Replace the infinity with a finite upper limit b. Integrate, then take the limit. The antiderivative of 1 over x squared is negative 1 over x. Evaluated from 1 to b, that's negative 1 over b minus negative 1, which is negative 1 over b plus 1. Now let b go to infinity. The term negative 1 over b vanishes, and you're left with exactly 1. The integral converges, and its value is 1. Pause on this. The curve y equals 1 over x squared extends from x equals 1 all the way out to infinity. There's no rightmost point, and yet the total area under it, a region that stretches infinitely far horizontally, is exactly 1 square unit, finite, bounded. That's the first paradox of this episode. An object of infinite extent can have finite measure as long as it's thin enough fast enough. Second example, the canonical divergent improper integral. Compute the integral from 1 to infinity of dx over x. Apply the same definition. Replace infinity by b, integrate, take the limit. The antiderivative of 1 over x is the natural log of x. Evaluated from 1 to b, that's the natural log of b, minus the natural log of 1, which is the natural log of b. Now let b go to infinity. The natural log of b grows without bound. The integral diverges. The area under y equals 1 over x from 1 to infinity is infinite. Now compare the two examples. The function 1 over x squared converges to a finite area. The function 1 over x diverges to infinite area. Both functions are positive, both decay to 0 as x approaches infinity, and visually they look almost the same on a plot. But 1 over x doesn't decay fast enough. The lesson is sharp. It is not enough for an integrand to go to 0. The rate of decay matters. 1 over x decays like 1 over x, which is too slow. 1 over x squared decays 1 power faster, which is fast enough. The dividing line is somewhere between them. Where exactly? That's the p-integral table 2 slides from now. A side note on the slowness of the natural log. The divergence of the integral of dx over x is barely a divergence at all. The natural log of 10 to the 100, the number with 100 zeros, is about 230. It diverges, but at a glacial pace. That makes it the borderline case, the slowest possible logarithmic divergence. Third example, type 2. The integral of dx over the square root of x from 0 to 1. Here the interval is bounded, 0 to 1, but the integrand 1 over the square root of x blows up at x equals 0. Apply the type 2 definition. Replace the bad endpoint 0 by a positive t, integrate from t to 1, then let t approach 0 from the right. The antiderivative of x to the negative 1/2 is 2x to the 1/2, which is 2 times the square root of x. Evaluated from t to 1, that's 2 minus 2 times the square root of t. As t approaches 0 from the right, the second term vanishes, and we get exactly 2. The integral converges. The area under the curve y equals 1 over the square root of x from 0 to 1, a curve that spikes to infinity at the left edge, is exactly 2 square units. Finite. Compare with the integral from 0 to 1 of dx over x. Same setup, slightly different power. The antiderivative is the natural log of x. Evaluated from t to 1, that's negative the natural log of t, which goes to positive infinity as t approaches 0 from the right, diverges. The picture mirrors the infinite interval case. 1 over x is the dividing line, 1 over the square root of x converges, 1 over x squared diverges, the spike is too sharp. Same theme, different direction. There's a unified table for both directions. Time to systematize. Consider the family 1 over x to the p for varying p greater than 0. The same family, integrated over 2 kinds of intervals, from 1 to infinity for type 1, from 0 to 1 for type 2, gives a clean dichotomy. Here's the table. At infinity, the integral from 1 to infinity of dx over x to the p converges if and only if p is greater than 1. The value is 1 over the quantity p minus 1. If p is less than or equal to 1, it diverges. At 0, the integral from 0 to 1 of dx over x to the p converges if and only if p is less than 1. The value is 1 over the quantity 1 minus p. If p is greater than or equal to 1, it diverges. Notice the opposite directions. At infinity, big P good, you need the function to die off fast enough. Small p means slow decay, and infinite area piles up from the tail. At 0, the situation is reversed. Small p good, you want a mild spike, not a sharp one. Big P means a very sharp asymptote, and infinite area piles up near the origin. The mnemonic, at infinity, fast decay, near 0, slow decay, fast meaning p greater than 1, slow meaning p less than 1. And right at p equals 1, the logarithm, both integrals diverge. It's the exact dividing case, on the wrong side of the fence in both directions. This table is the most used convergence fact in analysis. You will reach for it constantly. Memorize it now. Why does the table look like that? It comes from a single antiderivative computation. For p not equal to 1, the antiderivative of x to the negative p is x to the 1 minus p over the quantity 1 minus p. Evaluated from 1 to b, we get the quantity b to the 1 minus p minus 1 over the quantity 1 minus p. The whole convergence question reduces to what does b to the 1 minus p do as b approaches infinity? If the exponent 1 minus p is negative, meaning p greater than 1, then b to the 1 minus p is 1 over b to a positive power, which goes to 0. The limit becomes negative 1 over the quantity 1 minus p, which equals 1 over the quantity p minus 1. Finite converges. If the exponent 1 minus p is positive, meaning p less than 1, then b to the 1 minus p itself goes to infinity. Limit is infinite, diverges. And at p equals 1, the antiderivative isn't a power, it's a logarithm, and the natural log of b diverges. So the entire table is the question, what is the sign of 1 minus p? One sign convergent, the other divergent, and the crossover p equals 1 catches the logarithm diverging on its own. The type 2 side at x equals 0 is the same computation with t approaching 0 from the right instead of b approaching infinity, and the sign flips, which is why the inequality flips. A short proof, a powerful conclusion. Most improper integrals you meet in practice have no elementary antiderivative. The Gaussian e to the negative x squared, 1 over the quantity 1 plus x to the fourth sine of x over x, none of these have antiderivatives you can write down. So how do you decide whether they converge? 2 tests do most of the work. The first is the comparison test, and it works like this. Suppose everywhere on your interval, f and g are both non-negative, with f less than or equal to g. Then, if the bigger one, the integral of g, converges to a finite value, the smaller one, the integral of f, also converges. You can't have more area under a smaller curve than under a bigger one. And contrapositively, if the smaller one, the integral of f, diverges, the bigger one, the integral of g, also diverges. It's exactly the squeeze principle, adapted to areas. Bound your unknown integrand above by a known convergent integrand, you've shown convergence. Bound below by a known divergent integrand, you've shown divergence. Example. We don't have a nice antiderivative for 1 over the quantity x squared plus 1 to the extent we want to use it for the integral from 1 to infinity. But for x greater than or equal to 1, we have 1 over the quantity x squared plus 1 less than or equal to 1 over x squared, and we just showed the integral from 1 to infinity of dx over x squared equals 1. So by comparison, the integral from 1 to infinity of dx over the quantity x squared plus 1 converges. We don't know what it equals from this argument, just that it converges to something finite. The point isn't to find the value. The point is to know existence. For analysis, that's often the whole question. The comparison test is great, but sometimes the inequality is annoying to set up. There's a slicker version called the limit comparison test. Set up f and g, both positive on the interval from a to infinity. Suppose the limit of their ratio f over g as x approaches infinity exists and is a finite positive number, not 0, not infinity, just some honest positive constant. Then the integral of f and the integral of g either both converge or both diverge. Their convergence behavior is the same. The intuition, if f is asymptotically L times g for large x with L a finite positive constant, then for large x the function f is essentially a constant multiple of g. A finite multiple of a convergent integral is convergent. A finite multiple of a divergent integral is divergent. So they live or die together. Why is this useful? Because instead of fiddling with inequalities, you just compute a limit of a ratio, something we're already good at from intro calculus. Example. Consider the integral from 1 to infinity of the quantity 2x plus 3 over the quantity x cubed plus x plus 1 dx. For large x, the dominant behavior of this rational function is 2x over x cubed, which is 2 over x squared. So compare with g equals 1 over x squared. The ratio f over g equals the quantity 2x plus 3 times x squared over the quantity x cubed plus x plus 1, which as x approaches infinity approaches 2. A finite positive limit. We already know the integral of 1 over x squared converges, so by limit comparison, our integral converges too. In practice, this is the dominant move. For rational functions and similar, just look at the dominant asymptotic behavior, the highest powers. Compare with the appropriate p-integral, and you have your answer. 3 seconds of work. Fourth example, and a touchstone for everything that follows. The integral of e to the negative x from 0 to infinity. By the definition, integrate from 0 to b, get 1 minus e to the negative b, let b go to infinity. The exponential term e to the negative b vanishes, leaving exactly 1. Converges to 1. Exponential decay is qualitatively different from polynomial decay. The function e to the negative x goes to 0 faster than any polynomial 1 over x to the p, no matter how large p is. That's the famous exponential beats polynomial fact. It means the integral from 0 to infinity of e to the negative x dx converges in a stronger sense than the integral from 1 to infinity of dx over x squared does. The tail is more tightly bounded. Why does this matter? Because the gamma function, the continuous extension of the factorial, is defined by gamma of s equals the integral from 0 to infinity of x to the s minus 1 times e to the negative x dx. For every s greater than 0, the integrand is a polynomial, x to the s minus 1 times exponential decay. The exponential dominates as x approaches infinity and crushes the polynomial, ensuring convergence. The gamma function exists because exponential decay beats every polynomial. Same idea makes the normal distribution work, makes the Laplace transform work, makes most of probability theory go through. Exponential decay is the king of convergence. Fifth example, a classic. The integral of 1 over the quantity 1 plus x squared over the entire real line. Both endpoints infinite, we need to split. Split at 0. The right half, integrate from 0 to b, get arctangent of b minus arctangent of 0, which is arctangent of b. As b approaches infinity, arctangent of b approaches pi over 2. So the right half is pi over 2. By symmetry, the integrand is even. The left half is also pi over 2. Total, pi over 2 plus pi over 2 equals pi. That's already remarkable. The integral of a rational function, no trig in sight, equals pi. The reason pi shows up is that arctangent is in the antiderivative, and pi is the half revolution bound on arctangent. Now, the application. The function 1 over pi times the quantity 1 plus x squared, the original integrand divided by pi, is the density of the Cauchy distribution, a famous probability distribution in statistics. The normalization constant pi in the denominator is precisely because the integral of 1 over the quantity 1 plus x squared dx equals pi over the real line. You need to divide by pi to make the total probability 1. The Cauchy distribution is the heavy-tailed cousin of the normal, so heavy-tailed that its mean doesn't even exist. The integral of x times 1 over pi times the quantity 1 plus x squared dx diverges. But the distribution itself is a perfectly legitimate probability density, born directly from an improper integral with value pi. Why are improper integrals so important in practice? Because nearly every quantitative tail behavior in science is computed by 1. In probability theory, a continuous random variable has a density function p of x defined on the whole real line, and the total probability is the integral from -infinity to infinity of p of x dx equals 1. That equation is an improper integral with prescribed value. The normalization of the normal distribution, of the Cauchy, of the gamma, of every continuous distribution is an improper integral. Tail probabilities, the probability of an outcome greater than some threshold t, are the integral from t to infinity of p of x dx, an improper integral parametrized by the cutoff. The probability that a normal random variable exceeds 3 standard deviations is one of these integrals, evaluated numerically. Expected values, means, variances, moments, are improper integrals over the real line. For some distributions, like the Cauchy, these integrals diverge, meaning the distribution has no finite mean. The diagnostic for does the statistic exist is an improper interval convergence question. Special functions of mathematical physics, the gamma function, the beta function, the Laplace transform, the Fourier transform, the Mellin transform, all defined by improper integrals over various domains. Convergence of these integrals is the first thing you check when working with any of them. Calculus 2 treats improper integrals as a finishing topic. Applied math treats them as the foundation. A note on history. Improper integrals are where calculus became analysis. In the 1820s, Augustin Louis Cauchy gave the first rigorous treatment. He formalized the definition of the integral from a to infinity of f as a limit of finite integrals, and he separated the question of computing the integral from the question of whether it exists. Before Cauchy, this distinction was muddled, and people happily wrote down infinite area integrals without questioning whether the symbol made sense. In the mid-1800s, Dirichlet and Riemann sharpened the story. They distinguished absolute convergence from conditional convergence. An integral, the integral of f, converges absolutely if the integral of the absolute value of f converges too. Conditional means the integral of f converges, but the integral of the absolute value of f doesn't. The canonical example is the integral from 0 to infinity of sine of x over x dx. The positive and negative oscillations of sine of x cancel each other out at just the right rate to give a finite limit, pi over 2, beautifully. But the integral from 0 to infinity of the absolute value of sine of x over x dx diverges. Without the sign cancellations, it's harmonic-like and blows up. Conditional convergence is a delicate, almost paradoxical phenomenon. It's the source of Riemann's rearrangement theorem for series, and a sign that improper Riemann integration has subtleties even today. In the 20th century, Lebesgue gave a more powerful integration theory. In the Lebesgue framework, conditionally convergent integrals simply aren't integrable. The Lebesgue integral requires absolute convergence by definition. Conditional convergence becomes a feature only of the narrower Riemann theory. The improper integral question gets recast as, does the absolute value of f belong to L1 or only to some weaker space? All of that lives downstream of the simple calculus. Two-level definition we worked with today. Improper integrals are the first place in calculus where the question, does it exist, becomes non-trivial, and they're the gateway to all of modern analysis. Recap. Two kinds of improper. 1. Infinite limits of integration, where the interval has no right or left endpoint. 2. Unbounded integrand, where there's a vertical asymptote somewhere inside the interval. In either case, the Riemann definition doesn't apply directly, and we define the improper integral as a limit of ordinary integrals over shrinking and growing intervals. The integral converges if the limit exists and is finite. Otherwise, it diverges. The p-integral table is the most used convergence fact in analysis. The integral from 1 to infinity of dx over x to the p converges if and only if p is greater than 1. The integral from 0 to 1 of dx over x to the p converges if and only if p is less than 1. At p equals 1, both diverge. The mnemonic, at infinity, fast decay, near 0, mild spike. For integrals you can't compute, two tests. The comparison test, bound your integrand between known curves and squeeze. The limit comparison test, take the asymptotic ratio with a known p-integral, get a finite positive constant, conclude that your integral and a comparison integral behave the same way. 4 touchstone values, the integral from 1 to infinity of dx over x squared equals 1, convergent. The integral from 0 to 1 of dx over the square root of x equals 2, convergent type 2. The integral from 0 to infinity of e to the negative x dx equals 1. Exponential decay beats everything. the integral from negative infinity to infinity of dx over the quantity 1 plus x squared equals pi from nowhere, and the foundation of the Cauchy distribution. Carry those in your head. Next episode, area between curves. We step back into geometry and ask, given two graphs, what's the area they sandwich? It's a quick, satisfying topic, and a clean reset before we measure volumes and arc lengths. See you there. That's Improper Integrals. If this was useful, hit like, leave a comment, and consider subscribing. It really does help the channel reach more learners. Post your favorite improper integral below. Bonus points if the answer involves pi, e, or both. Those tend to be the most beautiful ones. Next episode, area between curves. After 3 episodes deep in convergence questions and integration tricks, it's nice to come back to plain geometry. Given 2 curves, what's the area they enclose? Quick, clean, very visual. See you there. Improper integrals are where calculus meets analysis. Where MAD does the area exists becomes a real question and not a trivial one. With the P integrals and the comparison tests in hand, you can decide convergence for most integrals you'll meet in the wild, including the central building blocks of probability and physics, the gamma function in TE0 and FDX to the s-1e minus x dx, the Gaussian in t minus and FDE minus x squared dx, the Cauchy in t minus and FDN FD dx si squared plus x squared. Next episode, we step back into geometry, area between curves, the signed area between 2 graphs, the natural extension of area under a curve's area enclosed by 2 area enclosed by 2 curves. A simpler topic, but a clean reset before we start measuring volumes and arc lengths. Subscribe. See you there. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.